Hello, this is Kerry Schutz from MathWorks, and in this video I'm going to talk about and show how to analyze a PLL in the phase domain using MATLAB. And it's actually a phase domain PLL, which we see here on my opening slide. Now, of course, it looks very much, and it's really indistinguishable from any feedback control system, but it just so happens to represent a PLL, in particular a charge pump PLL. Now, the phase domain modeling concept is nothing new. The phase domain models are essentially linear models that treat the phase lock loop as a control system, a feedback control system. The reference input and the VCO output both have units of phase in a phase domain model. That would be the input and output are either in units of radians or degrees. And phase domain PLL models assume an initial locked state. And that means essentially that the VCO frequency is locked already to the n times the reference frequency. And now in such a phase domain model, it's only the phase of the reference that's going to vary, not the frequency. And we're going to call that variation phi ref of s, or theta, I should say theta ref of t, depending on whether we're working in the Laplace domain or in the time domain. There is also, I list down here, a link in the doc, in our MathWorks doc, that talks more about phase domain models, and I'll just go over here and call that page up. I'll just call that up. You can see its name, the link in our to it in our doc, and then what it says about modeling PLLs in the phase domain there. This just so happens to come from the mixed signal block set portion of the MathWorks documentation, but you won't need the mixed signal block set in order to look at this doc that I'm showing on the screen right now. You just need to go to this link, this URL. And in there, it'll talk about, well, the term phase domain refers to representations of a periodic signal in terms of its phase with respect to an ideal reference with the same period. Okay, and you can go through, and it goes through lots of details of, the modeling aspects here below. Okay, I won't go through that. I'm going to give you my own kind of take and version of that here in this video. And pictorially, it might go something like this without getting into all the math. A time domain model here we have at the top. It shows the different constituents, building blocks of a charge pump PLL. We've got a phase frequency detector, and then on this icon you have some representation of how that circuit is actually built in practice. You see a dual D flip-flop structure with feedback loops through a gate to a reset. For the charge pump, we see current sources. It might be NMOS and PMOS, and we've got switches, which would be transistors in practice as well. We've got a loop filter. It could be active or passive. We're showing a third order passive filter here composed of R's and C's, or if it was active, it'd have op amps as well. The VCO could be like an LC tank tuned VCO. It could be a ring oscillator VCO. And underneath all these blocks, we've got some type of detailed behavioral representation of those circuits, again, including the divider, which would be some type of a digital counter flip-flop implementation, again. But you can go to quite a bit of trouble, even if it's not the actual silicon. You can have very, very detailed models of these in your simulation environment. This screenshot just so happens to come from mixed signal block set, but it could come from a textbook or any other environment. In any case, you see that the input is a square wave of some frequency, and the output is n times that frequency. But again, it's a voltage versus time periodic waveform. Now, what we see at the bottom is, instead of inputting, let's say, this first harmonic approximation of this square wave input, again, the full waveform would be a sum of odd order sine waves of decreasing amplitude. With a first harmonic approximation, you would just filter out the higher order sine waves and just be left with sine of 2 pi f ref times t, where f ref is the frequency of this square wave, and then plus possibly some phase variation or phase modulation about that frequency. Now, what we're going to do in the phase domain model is just strip away all of that, strip away the higher harmonics, strip away the sine of 2 pi f ref t, and we're just going to leave ourselves with that phase perturbation, theta ref of t, or theta ref of s if we're in the Laplacian domain. And that has implications on the rest of the phase domain model, or the rest of the PLL model itself. So if you change the input, we've also got to correspondingly make the if the input's going to be a phase, now the implementation or the model must reflect that as well. In fact, it gets quite simple when you do that. The phase frequency detector, instead of this kind of detailed circuit implementation, becomes just a differencing operator followed by a simple gain, in this case 1 over 2 pi. That's a nice simplification. The charge pump, instead of the current sources and switches, just becomes a simple gain. Again, in this case, 5 milliamps, reflecting the value of that current source. The loop filter, in this case, just becomes a simple Laplacian transfer function, a ratio of polynomials in S. And of course, that ratio depends on which particular loop filter architecture you're choosing, active or passive, and what order it is. In this case, it's third order. And this is the particular transfer function in all symbolic form. And if you substitute in some circuit values, or component values, you would get a certain loop filter transfer function. Now, this video, I'm assuming that all the design has already been performed, and we are simply implementing it, simulating it in whatever tool we're using here. I'm using MATLAB today. The VCO, again, reduces to some type of, resonant tank or ring oscillator to a simple gain and integrator. Now, one common question, that comes up, at least conceptually, is where did the integrator come from? Doesn't a VCO just map a voltage to a frequency? And yes, it does map a voltage to a frequency. It's a voltage-controlled frequency device. However, we don't want a frequency being fed back to our phase frequency detector. We want, in this case, a phase, because we need to compare phi ref to phi out. And in order to move from frequency to phase, we do need to integrate. That's just a mathematical requirement to move from frequency to phase. And so that's what's done here with the 1 over S. That's the, integration in the frequency domain. And then, of course, the divider simplifies from some type of, digital circuitry to a simple 1 over n multiplication operation. Again, all of the operations I'm showing here below are very, very simple to implement in any type of MATLAB or Simulink or any type of software model for that matter. You can see here what I'm showing is I've got a delta input in phase, some phase perturbation here from, let's say, phi start to theta start to theta end, maybe a small 1 degree phase shift. And then we're seeing what type of impact that has on the PLL output, again, in terms of phase. Now, there are, of course, pros and cons associated with those simplifications that I just made from moving from the time domain to the phase domain version. One of the pros is that the phase domain model is an excellent starting point for tuning loop dynamics and assessing phase noise transfer functions. So today we won't get into all the phase noise transfer function aspects of it, but it is very simple. I'll just say conceptually now, with a phase domain model, to model the to measure phase noise transfer functions by just modeling them as disturbances injected at different points in the phase lock loop, and then we'll look at the effect on the output in response to these different disturbances that are injected into the PLL model. Likewise, a phase domain model runs very fast, and one of the reasons it's running very fast is A, we've made a lot of simplifications on the model, and B, we're not trying to run it as fast of rate or sample rate, or not capturing as high bandwidth of dynamics as we would in a full time domain model. Typically, you'll run a phase domain model at some, let's say, low multiple of the loop bandwidth. If your loop bandwidth is 1 megahertz, you might run a phase domain model at 10 megahertz sample rate. Whereas with a full PLL model that's running at gigahertz, well, you need to have a sample time or sample rate that reflects that carrier as well. So the phase domain models are lower bandwidth models. Now, of course, that doesn't come without drawbacks or downsides. And one of the downsides, the obvious downsides of a phase domain model, is it doesn't actually produce or consume a clock. If you go back to the model here, it's producing a step in phase to a clock, but not the actual clock. So if you had a larger model that needed to, use the output clock that the PLL provided, well, the phase domain model is not going to get you there. It's just going to produce some, step, waveform. Another disadvantage of the phase domain model is that it's really limited to a single fixed frequency, assumed lock frequency. It can't model acquisition behavior. It can't model things like cycle slips, anything that depends on like a variable frequency behavior. That's not part of a phase domain model. Finally, with the phase domain model, it's difficult, I wouldn't say impossible, but more difficult to model circuit impairments as circuit impairments and to perform related spurious analysis, like charge pump mismatches or dead time in your phase frequency detector, things that are nitty gritty circuit details that you want to model. Those aren't easy to insert in a phase domain model. Again, not impossible. If you go to extra modeling trouble, you can do it, but not as obvious or easy how you would do that. And one of the reasons also that it's not easy to perform things like spurious analysis well is because you're typically not running this goes back to the whole sample rate. You're not going to run a phase domain model typically at a super fast rate. And so you're going to be limited in bandwidth. And that means that spurs typically occur at, multiple harmonics out, which would, be a much larger bandwidth than you would typically be simulating such a phase domain model. So again, great starting point, runs fast, but has limitations in terms of fidelity. So in this video, I'm going to concentrate on analyzing a charge pump PLL, and I'll be using only really base MATLAB features. However, I will use Control Systems Toolbox and maybe Symbolic Toolbox, we'll see, as just a reference point. We won't be leveraging them in any intense way, but we will be using Control Systems Toolbox since it's typically a tool at our disposal. It's something that many of us have grown to use and trust over the years. So I'm going to compare my base MATLAB analysis method with Control Systems Toolbox method. All right, so let's go ahead and jump over into the tools. Okay, so now we are over in MATLAB. In particular, from MATLAB, we have opened up our live editor. Within live editor, I've got my live script, which is doing my PLL analysis using MATLAB. The goal of this exercise is to compute the frequency response and the step response of our charge pump PLL phase domain model using these linear assumptions. To do so, we're first going to use the aid of Control Systems Toolbox functions, and then we're going to do the same thing except without using those Control Systems Toolbox functions. This exercise does assume that the PLL parameters have already been chosen/designed. So all we're doing is, shall we say, putting them in the model. These are the same screen captures we had in our PowerPoint presentation earlier you saw. The only thing I'll note is that we are again deriving the closed loop transfer function of the PLL phi out of S over phi ref of S. That's our phase transfer function. All right, so let's start with the number one, which is computing and plotting the frequency response using Control Systems Toolbox functions. Okay, so let's just start using those functions. In Control Systems Toolbox, you'll find functions like TF. Here's another use of TF. Here's a use of the feedback function and the Bode function. So those are the Control Systems Toolbox functions we're using, along with the step function. So all of those we're leveraging from Control Systems Toolbox to help us model this PLL in the phase domain. So you'll see things like KP, KC, LF for loop filter, VCO, and divider. So here we go. We got our charge pump current. Charge pump model then reduces to just a single scalar, our gain of 5e minus 3 or 5 milliamps. The numerator and denominator of our loop filter based on the architecture and the components that we've chosen are as follows. And so we create a loop filter Control Systems Toolbox transfer function object reflecting that. We create this is our VCO gain in hertz per volt. You notice you don't see a phase detector gain of 1 over 2 pi here because the gain of the phase detector and the gain of the VCO cancel out. There's a 1 over 2 pi factor in the phase detector. There's a 2 pi factor in the VCO, so we just those just kind of self cancel out. And now we're left with, each of the gains for each of the constituent blocks. We've connected them together via a feedback function. So we've got Kc times Kvc over S times the loop filter, and then the feedback gain of 1 over N. And then we've got a control systems toolbox closed loop representation. I'm calling it H underscore CST for H closed loop transfer function and CST for control systems toolbox. And that's pretty much it for the entire transfer function of the PLL and the Laplacian domain using control system toolbox. Now, in order to do analysis on that, typically I'll say the bandwidth I care about is maybe 20 megahertz in radians per second. That would be times 2 pi. And then I use the Bode function to get the magnitude, to tease out these respective magnitude and phase responses. And then I just compute magnitude here, 20 log 10 absolute value, and the phase, well, phase already came out. I just do a simple unwrap here below and plot those out along with the step response. So I apply step and Bode to this derived H underscore CST, the closed loop phase transfer function, plot those out, and I'll do that by running this section of code. In Live Editor, I'll just hit run section. And when I do that, I get an error. That's because I didn't run the first section. Let's run the first section first to define that variable, run in advance. Then I'll run the second section, run section. We'll see if it, and now here we go. So now we've got the magnitude response closed loop of the PLL. You see it's got a peak of about 3 or 4 dB of peaking around 1 megahertz. And then we've got the phase response of the PLL, and we have the step response where we see it settles around 70, which is just happens to be the divide factor in the PLL. So that's an easy way to kind of get a gut feel if your PLL is settling at the right value. For an integer in PLL, it should settle at steady state for a phase domain model, it should settle at the divider factor, assuming you're putting a unit step in. Okay, so that all seems to make reasonable sense. Now, what if we wanted to do the same thing without leveraging, those transfer function objects and step response functions and feedback functions? How would we do that? Well, the answer boils down to really 2 things in base MATLAB. It would be polynomial multiplication in Laplace and inverse FFTs. So we're going to leverage both of those capabilities of base MATLAB to do the same type of control systems analysis. I'm going to set, first of all, I'm going to create some variables here. In other words, how long am I interested in analyzing the step response over? I'm just going to initially choose 10 microseconds. What bandwidth am I interested in? I'm going to say a frequency range of interest similar to above is 20 megahertz. But now if I'm going to analyze something over 20 megahertz, and I'm going to do any type of discrete time analysis, like the FFT, I'm going to need to pick a sample rate. Well, by Nyquist theory, you'd have to choose at least 2 times 20 megahertz, but I'm going to be very, very conservative and go much faster. I'm going to say 10 times the bandwidth is going to be my sample rate. Again, you can play with that and see what the side effects or trade-offs of a faster, slower sample rate is, or oversampling factor of 10. So using that FS, that corresponds to a sample period of 1 over FS. And that also corresponds to this many number of points in my analysis. Again, we're assuming we're doing a fixed step kind of discrete time analysis. So that would be the length of the simulation times the sample rate. And that comes out to be, well, I haven't run this yet, but if I run it, I can find out real quick that number of points is around 2,000. Okay, so if we go down, we're going to next compute the spacing and frequency of our analysis, and that's nothing more than the sample rate divided by the number of points. Our FS in this case is 200 megahertz, and our number of points is 2,000, so our DF becomes 100 kilohertz. I take the spacing and frequency, our DF, or delta F value, and I create a frequency vector from it that starts at DF in DF steps, all the way up to DF times the number of points minus 1. And so that's essentially going up from 100 kilohertz and 100 kilohertz steps all the way up to 100 kilohertz times, 2000 or 1999 in this case. All right, approximately up to 200 megahertz. And of course, if I'm only interested in the positive half of the frequency range, so I just clip off the first half of that vector going from up to Nyquist. And I also, you notice I trim out DC. I didn't put 0 to DF here, and that's because I'm going to be later. I'm going to be dividing by S or F, a frequency variable. I don't want to be dividing by 0, so I handle DC separately. All right, and then I create a complex frequency vector, which is the Laplacian S, SL, which is J times 2 times pi times our frequency vector. Because the frequency vector is real, SL is complex, or the complex S variable. So this node is different. This is just a MATLAB variable, complex MATLAB variable. This is not the same thing as above, where I created this sort of symbolic control systems toolbox S variable up here. Okay, so if I were to look at HCST, which I did earlier, I just put this in MATLAB, H underscore CST is this symbolic-ish, it's not symbolic toolbox, but it's symbolic-ish control systems toolbox transfer function of the PLL, the closed loop transfer function. Now, this is going to be very different from what I did here below, where I created this complex frequency vector, SL. So it's 1,000 points long, SL is. And if I were to just type it out and let it run over my screen here, I'll do it transpose so we can see it. We can see that it's a bunch of complex frequency values. Okay, it's not symbolic. Okay. So now I'm going to take, and now using that complex frequency vector SL, I'm going to now compute the responses by using polynomial multiplication of each of the individual blocks. For instance, starting with the loop filter, I'm going to take the numerator and denominator coefficients, that's, again, redefined right here, and I'm going to be multiplying that numerator and denominator, right? I'm going to do the same thing I just showed here in using Control Systems Toolbox, this one right here. I'm going to essentially do this, except I'm doing it empirically. I'm going to substitute in SL right here, right here, right here, right here, and right here, okay? So I'm doing that in this transfer function you see right here below. Of course, this is for the closed loop. If I were to do it just for the loop filter, it would be a little different. It would be Z underscore LF. I'll just do that just so I'm speaking consistently, Z underscore LF. And that is the, let me do that again one more time, do here. This is the loop filter transfer function in empirical terms, okay? All right, so we've got that. Now we've also got the open loop transfer function of the PLL. We've got this KC charge pump times KVCO times Z squared left divided by S, okay? And likewise, we've got now finally the closed loop transfer function manually derived of the PLL. And now comes a little care must be taken. I'm going to insert the DC point manually. So my previous analysis, remember my frequency vector did not have DC in it. I skipped DC. So I'm going to reinsert DC here. The DC response is just in the divider factor. And then I reinsert a DC frequency value here of 0 in the frequency vector, and I call that the manually derived closed loop response and the manually created frequency vector associated with that response. And then I take the magnitude of it, 20 log 10 absolute value, and then I plot that and compare it against the control systems toolbox derived a magnitude response. And you can see they overlay quite nicely here. Okay. Now, the next thing I want to do, and I say, okay, well, that seems pretty good, but can I get the step response from this empirically created closed loop transfer function H underscore CL underscore man? And that's what I do in the next step. Now, how do you go from a frequency response to a step response? Well, one of the things we can do here is take advantage of the inverse FFT. But the inverse FFT, really, it needs a full frequency spectrum, not a 0 to Fs over 2, but really a minus Fs over 2 to a plus fs over 2. And that's what I do in the first step here. I create this conjugate symmetric spectrum. I take the positive 0 to fs over 2 spectrum, I take the mirror image of it, conjugated, and that forms the rest of the frequency spectrum, the negative portion. But I'm taking, again, special care here, once again, to omit the DC point. We only have one DC point, and it's at the first value of this vector. And I omit the Nyquist point, and that's the last point of H underscore CL underscore man. And so omitting those points, then this becomes my conjugate symmetric frequency response or spectrum. At that point, then I can take the inverse FFT. I tell them it's symmetric, so I get a real impulse response output, manually derived. And I create a time vector, and then I can either plot out the impulse response, or I can integrate it, do a cumulative sum on it, to form the step response. And then I plot that out, and that's what we see below here. Now, likewise, I can compare all these and plot them on top of each other, and there's a final section in here, right here, which does that. I'll run this section. And once I do that, we're going to see the magnitude responses overlaid, control systems toolbox approach versus manually derived, and then the step response, likewise, accordingly. You can go in, you can click on these plots in Live Editor, and you can zoom in, and you can see that there's actually two waveforms there. They're just very, very, very close together. Okay, I hope that was helpful. This is my, again, my video attempt at explaining phase domain models and how you would model them using MATLAB. Now, in the future videos, I'm going to get into using Simulink for modeling phase domain and time domain models of PLLs, but that is for another day. In the meantime, thank you for tuning in here.